Chapter 12 of The ABC of Atoms. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Usha. The ABC of Atoms by Bertrand Russell. The New Physics and the Wave Theory of Light. In the physics of the atom, as it has become in modern times, everything is atomic, and there are sudden jumps from one condition to another. The electron and the hydrogen nucleus are the true atoms both of electricity and of matter. According to the quantum theory, there are also atomic quantities, not of energy, as was thought when the theory was first suggested, but of what is called action. The word action in physics has a precise technical meaning. It may be regarded as the result of energy operating for a certain time. Thus, if a given amount of energy operates for 2 seconds, there is twice as much action as if it operated for 1 second. If it operates for a minute, there is 60 times as much action, and so on. If twice the amount of energy operates for a second, there is again twice as much action, and so on. If the energy which is operating is variable and we wish to estimate its action during a given time, we divide the time into a number of little bits, during each of which the energy will vary so little that it may be regarded as constant. We then multiply the energy during each little interval of time by the length of the interval and add up for all the intervals. As we make the intervals smaller and more numerous, the result of our addition approaches nearer and nearer to a certain limit. This limit we define as the total action during the total period of time concerned. Action is a very important conception in physics. From the point of view of theory, it is more important than energy, which has been deposed from its eminence by the theory of relativity. Planck's quantum H is of the nature of action. Thus, the quantum theory amounts to saying that there are atoms of action. So long as we confine ourselves to what goes on in matter, this theory is self-consistent and explains the facts, nor is it easy to suppose that any theory which was not atomic would explain the facts. But when we come to what goes on in empty space or in the ether, we find ourselves in difficulties if we adhere to the quantum theory. Consider what happens when a wave of light is sent out by an atom with only one quantum of action in each period. The wave spreads out in all directions, growing fainter as it goes on, like a ripple when a stone is dropped into a pond. The evidence that light consists of waves remains quite unshaken. It is derived from the phenomena of interference and diffraction. As to interference, a few words may be necessary. If two sets of waves are traveling more or less in the same direction, if their crests come together, they will grow bigger. But if the crest of one comes in the same place as the trough of the other, they will neutralize each other. Now, it is possible to arrange two sets of light waves so that in some places their crests come together, while in others the one covers the trough of the other. When this is done, we get a lattice pattern of alternate light and darkness, light where the waves reinforce each other and darkness where they neutralize each other. If light consisted of particles traveling and not of waves, this phenomenon, which is called interference, could not take place. The difficulties which arise for the quantum theory out of the phenomenon of interference have been forcibly stated by Jeans in the following paragraphs. If light occurred only in quanta, interference could only occur at a point at which two or more quanta existed simultaneously. If the light was sufficiently feeble, the simultaneous occurrence of two or more quanta at any point ought to be a very rare occurrence, so that all phenomena such as diffraction patterns which depend on interference ought to disappear as the quantity of light present is reduced. Taylor has shown that this is not the case. He reduced the intensity of his light to such an extent that an exposure of 2000 hours was necessary to obtain a photograph, and yet obtain photographs of diffraction patterns in which the alternation of light and dark appeared with undiminished sharpness. In Taylor's experiment, the intensity of light was about 1 light quantum per 10,000 cubic centimeters, so that if the quanta had been concentrated, nothing of the nature of a diffraction could possibly have been observed. Thus, it appears that there is no hope of reconciling the undulatory theory of light with the quantum theory by regarding the undulatory theory as being, so to speak, only statistically true when a great number of quanta are present. One theory cannot be the limit of the other in the sense in which the Newtonian mechanics is the limit of the quantum mechanics, and we are faced with the problem of combining two apparently quite irreconcilable theories. Other similar difficulties might be mentioned, but the difficulty of interference may suffice since it is typical. It may be questioned whether the difficulty still exists when the quantum theory is stated in the form which it takes in Sommerfeld's work. We no longer have little parcels of energy. What we have is a property of periodic processes. It would not be accurate to state this property in the form: the total action throughout a complete period of any periodic process is h, or an exact multiple of h. But although this statement would not be accurate, it gives, as nearly as is possible in non-mathematical language, a general idea of the sort of thing that is affirmed by the modern form of the quantum theory. In order to reconcile this principle with the facts about the diffusion of light, it is only necessary to avoid dividing the ether into imaginary particles. As the light wave travels outward, so long as it meets no obstruction, its energy remains constant, though it is more diffused so that there is less of it in any given area of the wavefront. But while we remain in empty space, the wave must be treated as a whole, and the quantum theory must not be applied to separate little bits of it. The quantum theory has to do not with what is happening in a point at an instant, but with what happens to a periodic process throughout its whole period. Just as the period occupies a certain finite time, so the process occupies a certain finite space. And in the case of a light wave traveling outward from a source of light, the finite space occupied by the process grows larger as it travels away from the source. For the purposes of stating the quantum principle, one period of a periodic process has to be treated as an indivisible whole. This was not evident at the time when Jean's report was written, 1914, but has been made evident by subsequent developments. While it makes the quantum principle more puzzling, it also prevents it from being inconsistent with the known facts about light. It must be confessed that the quantum principle in its modern form is far more astonishing and bewildering than is its older form. It might have seemed odd that energy should exist in little indivisible parcels, but at any rate it was an idea that could be grasped. But in the modern form of the principle, nothing is said, in the first instance, about what is going on at a given moment or about atoms of energy existing at all times, but only about the total result of a process that takes time. Every periodic process arranges itself so as to have achieved a certain amount by the time one period is completed. This seems to show that nature has a kind of foresight and also knows the integral calculus, without which it is impossible to know how fast to go at each instant so as to achieve a certain result in the end. All this sounds incredible. No doubt, the fact is that the principle has assumed a complicated form because it has forced its way through owing to experimental evidence in a science built upon totally different notions. The revolution in physical notions introduced by Einstein has as yet by no means produced its full effect. When it has, it is probable that the quantum principle will take on some simple and easily intelligible form. But it will only be easily intelligible to those who have gone through the labor of learning to think in terms of modern physical notions rather than in terms of the notions derived from common sense and embodied in traditional physics. In the last chapter of this book, we shall try to indicate the sort of way in which this may affect the quantum principle. It is necessary, however, to utter a word of warning in case readers should accept as a dogmatic ultimate truth the atomic structure of the world which we have been describing and which seems at present probable. It should not be forgotten that there is another order of ideas temporarily out of fashion, which may at any moment come back into favor if it is found to afford the best explanation of the phenomena. The charge on an electron, the equal and opposite charge on a hydrogen atom, the mass of an electron, the mass of a hydrogen nucleus, and Planck's quantum all appear in modern physics as absolute constants, which are just brute facts for which no reason can be imagined. The ether, which used to play a great part in physics, has sunk into the background and has become as shadowy as Mrs. Harris. It may be found, however, as a result of further research that the ether is after all what is really fundamental and that electrons and hydrogen nuclei are merely states of strain in the ether or something of the sort. If so, the two elements with which modern physics operates may be reduced to one and the atomic character of matter may turn out to be not the ultimate truth. This suggestion is purely speculative. There is nothing in the existing state of physics to justify it. But the past history of science shows that it should be borne in mind as a possibility to be tested hereafter. If the possibility should be realized, it would not mean that the present theory is false. It would merely mean that a new interpretation had been found for its results. Our imagination is so incurably concrete and pictorial that we have to express scientific laws as soon as we depart from the language of mathematics, in language which asserts much more than we mean to assert. We speak of an electron as if it were a little hard lump of matter, but no physicist really means to assert that it is. We speak of it as if it had a certain size, but that also is more than we really mean. It may be something more analogous to a noise, which is spread throughout a certain region, but with diminishing intensity as we travel away from the source of the noise. So, it is possible that an electron is a certain kind of disturbance in the ether, most intense at one spot and diminishing very rapidly in intensity as we move away from the spot. If a disturbance of this sort could be discovered which would move and change as the electron does and have the same amount of energy as the electron has and have periodical changes of the same frequency as those of the electron, physics could regard it as what an electron really is without contradicting anything that present-day physics means to assert. And of course, it is equally possible that a hydrogen nucleus may come to be explained in a similar way. All this is, however, merely a speculative possibility. There is not as yet any evidence making it either probable or improbable. The only thing that is probable is that there will be such evidence, one way or other, for many years have passed. End of chapter 12. Read by Usha, March 6, 2021.